My work, a CMOS chip with multi-junction photodetector for sensing biomedical signals. I'm with the Institute of Electrodynamics, Microwave and Circuit Engineering of the Vienna University of Technology. And the following talk will be outlined as follows. Firstly, I will shortly present the motivation behind my work. Then I will go into the detail of the used wavelength-dependent photodetector. And I will shortly present the proposed sensor system and how it will be used for sensing biomedical signals. I will present results from the electrical point of view, and I will also present some measured biosignals. Finally, I will conclude my work. The motivation behind this work is that optical sensors are quite often used in biomedical applications because they are easy to use, they are robust, they are cheap. For example, optical plethysmograms are often used for detections, but conventionally they use only one photodetector at a time, and they time multiplex different kind of LEDs for detecting the biosignals. And at this work, we used a wavelength-dependent photodetector which employs 3 photodiodes. And with that, it is possible to get a simultaneous registration of the signals, and time multiplexing can be avoided. And we also placed an on-chip amplifier on this circuit to get a better signal-to-noise ratio and a high dynamic range. As I already mentioned, we used wavelength-dependent photodiodes, which employs 3 photodiodes on top of each other. But how to get a wavelength dependency? If you look at the penetration depths over the wavelengths, then you will find out that blue light penetrates silicon only for a few nanometers, whereas red and infrared light penetrates silicon quite far. And therefore, here in the figure is the absorption coefficient, and therefore blue light around 400 nanometers is more absorbed than infrared light at 1000 nanometers. And how to implement such a photodetector in a standard CMOS process? And why do we want to use a standard CMOS process? Standard CMOS process is cheap and easy to get, and therefore it's a good decision to use only a standard CMOS process. We use the triple well CMOS process, which means that you have isolated NMOS transistors, and with this configuration it is possible to implement 3 vertically stacked photodiodes. That means that you have a top photodiode, you have a middle photodiode, and a bottom photodiode. The first top diode is placed between the N+ region and the P-well region, the middle one between P-well and deep N-well, and the bottom one between deep N-well and P-AP. And these are all diffusions which are used for NMOS and PMOS transistors in this technology. So no process modification were used at all. And if you characterize this photodetector in the wavelength domain, you find out that you get 3 distinctive responsivities for each diode. The top diode is most sensitive to blue light, which also relates to the penetration depth of light in silicon. The middle one is most sensitive to the green light, as seen here, and the bottom one is most sensitive to red and near-infrared light, as can seen here. With these three distinctive peaks, it is easy to discern between the different wavelengths. And how looks our proposed sensor system? The detector and the amplifier are fully integrated. They are on one chip, as indicated here. We placed one LED on the opposite direction of the sensor. We use the transmittance mode, and the test subject, in our case a finger, was placed between the LED and the sensor. And the sensor is, there we have the three photodiode junctions, as indicated here, and each photodiode has its own amplifier. And what's important for these amplifiers, we needed a transimpedance amplifier which converts current into voltage, and instead of a linear feedback, like indicated here with just a feedback resistor, we opted for a nonlinear feedback to get a logarithmic transfer characteristics. And with that, it is easy to get a high dynamic range, which is very important for optical sensor applications. And this transimpedance amplifier also biases the photo detector, which is important because each photodetector junction must be reverse biased. And by applying external bias voltage here, you can assure that each junction is reverse biased. And what's the result? We made a test chip which is roughly 2 square millimeters big, and it has a 100 micrometer photodiode, as shown here in the red circle. The amplifier circuit is in the blue rectangle. And as you can see, the size of the photodetector and of the amplifiers is much smaller than the whole chip size. The chips are more or less pad limited because there are also ESD structures and decoupling capacitors on this chip. Because we used a standard CMOS process, it is easy to implement additional circuitry on this chip and not only this amplifier circuit. So it can be a system on chip could be realized where digital and analog circuits are combined. We measured the effective transimpedance depending on the photocurrent here. And we have noticed that the logarithmic law is followed over a wide range, from almost 1 milliamp to the nanoamp regime. This shows the wide dynamic range. The little noise here is just because of net hum and such things, and because noise measurements or measurements at the nanoamp regime gets a little bit complicated. But in principle, the sensor would be able to go further into the picoampere range. Now, finally, to the optical biomedical signals we measured. We measured a PPG signal with red light as an illumination source in the transmittance mode. And as you can see, many important biomedical features are clearly seen, like the fast systolic increase of the amplitude and the slow diastolic decrease. And also important features like the dichrotic notch can be seen. And as already mentioned, we have a wide dynamic range that even with the least sensitive channel for blue light is still able to get this signal. Yeah. Let me conclude my work. We presented in this work as CMOS sensor chip, which is implemented in the standard 350 nanometer process without any process modifications. We have shown that a multi-junction photodiode, which consists of 3 different photojunctions, can be used for a wavelength-dependent photodetector. And we integrated an amplifier on this chip, which has a wide dynamic range. And additional circuitry can be in the future easily implemented because it's a standard CMOS process. And we also showed that the ability to acquire biomedical signals. For example, we've shown here a photoplatismogram in the transmittance mode. Thank you.